All right. Hello, everyone. Welcome to my Python tutorial. This is Alex Berryhill, and today we are going to talk about stacks, sets, and trees. All right, to start off with stacks, a stack is just an order. It's not a physical or digital thing. It's an order of basically everything we do in programming. So the most common that I like to use would be an array. Now, stacks and arrays and everything else, they go by something called last in, first out. This means that the last thing that we put in is the first thing that comes out. That is, in an example, imagine we have just a pile of documents on your desk. You have been putting papers on the desk all day, and imagine you want to take off the last one. And obviously, the last paper that you put on is the first one on top. So that would be the last one in is the first one out. And in Python, we can use that to our advantage by using some methods called push and pop. Now, imagine this is our array of 1, 2, 3, 4, 5, and we want to, or we accidentally added a 6 using push. We can take that off because that is the last thing that we put on the stack. So we don't even have to specify that it is a 6. We can just say stack.pop and it'll take off the 6. And that is how the undo button works. If we add something to a stack, we can immediately, simply, without having to specify what word we put in last, just say take it off the top of the stack. Now, this is also how functions work. When defining functions, it doesn't really matter what order we do that in, because what really matters is the function stack. Now, we can declare these second, first, and third, and each one will print off their corresponding number. And where it really matters is declaring it first, first, second, second, and third, third, and it'll run in that order. Now here's an example of using the function stack to our advantage to go through a maze. Recursion is basically keeping track, is calling functions instead of functions, and the key point of using recursion is keeping track of where we call our functions so they run in the correct order. And here is a problem that you can solve on your own. I won't spoil you with the answer here, but I have the answer inside of my repository, which I will link in the description of the video. So just predict what this code will print. We add and pop various numbers along this code, and the solution will be here. Now onto sets. Sets are something of a unique thing. They're much like arrays, except that sets do not care about the order and remove automatically duplicates. Now, to add and remove to a set, it's simple enough. You just say, hey, add 6 or remove 5. And as you can see here, unlike the previous one with the stack and arrays, we do specify what we use, and it doesn't matter what order and what the stack looks like, because everything is inside of their own spots and it can remove it much faster, and because it knows exactly where 5, 6, 1, 2, 3, 4, where they all are. And that is because of this. Inside of our set, this is a set with a 1, 4, a 7, and an 8 in it. And it's possible to get this incredibly fast big O notation 1 performance by having the index be exactly what the number is. So if we wanted to check if 4 was here, we can just say, hey, is 4 there? And 4 is there, so it will return true. And we can check for a 3. And is a 3 there? No, so then it would be false. And it doesn't have to loop through checking if a 4 is here, or a 4 is here, or a 4 is here, a 4 is here, or a 4 is here, and then finally return. It can immediately jump straight to 4 because it knows that's where the index would be. Now, as you notice here, imagine if our array goes up to 900 million, and I have only two things, a 0 and a 900 million. That would have an almost completely array, but take up a ton of space. And this causes a problem. So we can use something called a modulus. Now, a modulus is, to keep it short because that's not what we're learning right now, is just the remainder after dividing by a number. And it is a clever way of keeping something to a specific size. I will continue to cover that a bit later. But now that we have it as the correct size we want, now we want to store more than just simple numbers. Because as you can see here, these do not have decimal spaces or words, which is something that we would like to use inside of these sets. And that is where something called hashing comes into play. Hashing is simply a function that turns various items like strings and floats into integers that we can store inside of a set. And so instead of looking like this, now it looks like that. And here's an example of saying having a set of words where it says this is a string, except it's funny because it's not in that order. So, as you might notice, if you've ever had to use modulus before, is that this can create some conflicts. And when there are conflicts with the exact same address, there are two ways that we can solve this. One is called open addressing, and the other is called chaining. With open addressing, we can run it like this. So here's a quick thing with modulus. 0 modulus 5 is 0, and going on. But as you can notice here, 1 modulus 5 is 1, but 6 modulus 5, which is the list length, also equals 1. So this is where we run into our problem. We have our list of 5 length, 1, 2, 3, 4, 5, counting 0. But 1 and 6 run into the same spot. So now we have a conflict. Now there are two ways. First is the open addressing. It will move to the right to find the first open spot, because as we see here, 2 is open, and it moves over. Now, in chaining the values like that, there's another way we can do this, and this is called chaining, where instead of moving stuff over and checking for the next open spot, we simply just create a list, like an array, inside of our set. So both 1 and 6 are on side of 1, and 2 is left empty. Now here's our example. In our example, we imagined an imaginary company This company wants to pay for a user to finish certain tasks, but they do not want to pay for the user to do the same thing twice. And they want searching through these tasks to be extra quick. So in our example here, we have a set called commissions. And in our example, we have it listing through the commissions to read off the various commissions that the user has already finished. But the thing is, we also need it to store commissions for this employee, and that's up to you to write. Now, there is a solution, but the code, again, will be inside of the repository that I'll link in the description. Now, the third and final thing that we are running through today is something called trees. Trees are a lot like something called a linked list. If you do not know what a linked list is, it is kind of like an array, except it's created of a series of nodes that link to each other, much like this. So when you call the left, it goes to the left, and when you call the right, it'll go to the node on the right. And there are several types of trees. This doesn't cover all of them, but these are the ones that we're going to cover today. There's binary trees, there's binary search trees, and there are balanced binary search trees. The biggest difference between these trees and linked lists is that a tree can contain multiple nodes. We won't really cover that today, but this is something like what it would look like, where the node will connect to 4 other nodes, and it can create many branches. Now, here are the types of trees. We'll start with binary trees. A binary tree is a tree with only 2 children. So in this case, it's a left and a right. A child is a node that is connected to the parent node, which is the node that we are currently on. And it's connected to these 2 children nodes that look the same as the parent node. And we can sort this. And if we sort it like if the numbers that are smaller go to the left of the root and the numbers larger than the root, which is the original node, the first node put into the tree, they can go to the right. And now that it is sorted, it's called a binary search tree. And the way we can insert this data looks a lot like this, where the data that is smaller keeps going to the left until we find our empty spot. Or if the data is bigger, then we keep going to the right until we find our spot. Now, we may want to use this. Right. In a balanced search tree, we might notice that imagine if our first data is a 1, and then we want to count up from there. That would be a very uneven tree, and it'll be no better than just a normal list. Searching through this, maybe even slower. And if we want to organize this and keep both sides of the root equal, that's what we call a balanced binary search tree. And in that way, our big O notation, which is the speed of our search algorithm, will be O log n. And if you don't understand big O notation, that is very good, one of the best kinds of search algorithms other than our set. which is 01. But beyond that, using our binary search tree, we need to do at very least two things. We need to put stuff into our search tree, and we need to go through our search tree. So this is the same stuff that we covered earlier. Putting stuff into a binary search tree basically puts an item to where it needs to be sorted. So everything is from lowest to highest. And we can use something called hashing that we covered in our last section as well to get items sorted like this as well. Now, this is the most simple way to loop through our data, and this will just return all of our data. And we can also use this same data or similar data to check to find our object. But I won't spoil that for you because I would like you to write it yourself in our problem to solve to find where an item is contained inside of our binary search tree. In this example, this time the quote-unquote company wants to store and retrieve data, but its current search algorithm is not that great, and they want to switch over to a binary search tree. So in our example, we store data into the binary search tree, and we do that by inserting it. And while we insert it, we sort it into the correct spot so that we can find it easily or easier. Now, using this sorted data, search for this number that we will provide for you. So we'll insert these numbers, and we want you to check and return if these are in or not in the binary search tree. And again, the solution will be on the markdown. All right. Thank you for listening to my Python tutorial. If you have any questions, you can contact me at ber18020@byui.edu. And I will see you next time. Thank you for watching.